Alright, so now we're on to solving exponential and logarithmic equations. Okay, so we'll start off by talking about how we solve exponential equations, then we'll talk about logarithmic because they're actually very similar. So in this very first problem though, 10 to the x equals 1,000. So we could solve this without using any special rules. 10 to what power equals 1,000? 3. 10 to the third power is 1,000. So right now we'll just say, okay, x equals 3. Well, the key concept that we're looking for in exponential equations is if b to the x equals b to the y, then x equals y. So looking back at that example, I could rewrite 1,000 as 10 to the third. So 10 to the x, I'm going to rewrite 1,000 as 10 to the third. So since these have the same base of 10, I can just set their exponents equal to each other. X equals 3, which is what we got whenever we just solved it regularly. Okay, so we're going to try and solve these exponential equations. 7 to the 2x plus 1 equals 7 to the 3x minus 2. Alright, and because there's an exponential and only an exponential on each side of the equation, then we can solve by equating their exponents, as long as they have a common base. Both of these are base 7, so what do I know about these exponents? They're equal to each other. So I can just say, okay, 2x plus 1 is equal to 3x minus 2. And then I just go about solving for x. So I can add 2 to both sides and subtract 2x. So I'll add 2 first. 2x plus 3 equals 3x. Subtract 2x, 3 equals x. In b, we have 3 to the 2x minus 1 equals 27 to the x. The problem here is that the bases aren't the same. So we're going to have to form a common base. Sometimes forming a common base can be quite a challenge. In this case, 27 is a power of 3, like it's 3 to the third power. So I can write this as 3 to the 2x minus 1 and rewrite 27 as 3 cubed to the x. Now that we have a power raised to a power, the 3 and the x just multiply. Okay, so we have 3 to the 2x minus 1 equals 3 to the 3x. Now that their bases are the same, we can set their exponents equal to each other. Also, just for future reference, be careful. If this had something else attached to it, like a minus 2, you'd have to distribute the 3 to everything. But here we have 2x minus 1 is equal to 3x. Subtract 2x from both sides to get negative 1 is equal to x. Okay, so now we're going to solve this exponential equation. 4 to the x minus 2 equals 1. The difference here is that we just have one exponential. It's not an exponential set equal to another exponential, right? So what I'm going to try and do is I'm going to isolate this exponential. I'm trying to isolate 4 to the x. So right now there's a minus 2. How do I get rid of that minus 2? I add 2 to both sides. So now I have 4 to the x equals 3. Okay, now here's the problem. We have an x in the exponent. The only way to solve whenever you have an x in the exponent is to change it to a logarithm. How do we change these things to a logarithm? We just rewrite them in a different way using that loop. So the base of the log is going to be the base of the logarithm. Start it with this 4, go around the equal sign. So now I have log base 4 of 3 is equal to x. Now this is something that I can actually evaluate. If I have log base, with a number of a number, I can figure out what this is equal to using change of base. Okay, yeah, so we're solving it using change of base. The reason that we have to use change of base is because our calculators are all common logs. They're all base 10. So I have to make both of these base 10. So I go the log of 3 divided by the log of 4 equals x. Okay, that's the change of base formula. So x is equal to 0.792. And this should make sense. 4 to the 0.792. So it's less than 1 would equal 3. Because 4 to the first power is 4. So 4 to the 0.792 equals 3. There we go. And the next example, 150 e to the 0.05x equals 340. The first step is to isolate the exponential. And this one could be a little bit trickier, but this is my exponential right here. So right now it's being multiplied by 150. How do I get rid of that 150?
No, you do the...
I divide both sides by 150. So I have e to the 0.05x equals about 2.26. Now that I have the exponential by itself, I'm ready to do the loop. So go start with the base, go around. Alright, so we have log base e of 2.26 equals 0.05x. But hold on, log base e, what is this? That's just the natural log. So I end up with the natural log of 2.26, which my calculator will tell me equals 0.05x. So the next step, I'm just going to go ahead and divide by 0.05. Okay, so x is equal to the natural log of 2.26 divided by 0.05, which is about 16.307.
So you see...
Alright, in the final example, I'm trying to get my exponential by itself. There's a minus 2, so I'm going to add 2 to both sides. To get 4 to the x plus 2 equals 14. Alright, even though the exponent has some other things in it, the exponential is by itself. So what's the base of the exponential? 4. I'm going to start my loop there. Go around the equal sign. So I have log base 4 of 14 equals x plus 2. Alright, so we just saw how to evaluate this. We're going to evaluate that with change of base. And then to get x by itself, I'm also going to have to subtract 2. So I can use change of base, log of 14 divided by the log of 4. Whatever this is, minus 2 will equal x. Okay, so the minus 2 needs to come later. And that gives us x is about negative 0.096. Alright, so now we're going to switch gears into solving log equations. But almost all of the rules are the same for log equations as they were exponential. Like with exponential, if you had two bases being raised to the to exponents, if the bases were the same, then the exponents must have been equal. Here, if you have log base b of x equals log base b of y, if these bases are the same, then x must equal y. So here we have log base 5 of 4x minus 7 equals log base 5 of x plus 5. Since they're both log base 5, well then 4x minus 7 must be equal to x plus 5. Okay, get your x's on one side. We'll subtract an x from both sides. And add 7 to both sides. To get 3x is equal to 12. Divide both sides by 3. And x equals 4. Now, one thing to keep in mind about logarithm equations, or logarithmic, is that think about their graph, right? So, like the parent function looks like this. The domain of this is always just x is greater than the asymptote. So, you're not not all of the answers will actually work. Sometimes we'll get extraneous solutions, and we're going to talk more about that in a little bit, but you should always be checking your answer by plugging 4, like here we plug 4 back in, and if at any point you would be taking the log of a negative, that's not defined. And we're going to talk about that in a minute. Now, if you don't have, two logs set equal to each other with the same base, like here we have just one log, well then we're going to have to use the same rules as we did for the exponential. We can't solve if we're taking the log of a variable, so we're going to have to rewrite this one as an exponential. It's all of the same steps. Just like getting the exponential by itself, our first step is to get the log by itself. So I'm going to add 1 to both sides first. So I've got log base 4 of 5x minus 1 is equal to 3. Now that I've got the log by itself, I can do a loop. We start with the base of the log, go around the equal sign. And you should see that now this is something that we could actually solve, because 4 to the third is equal to 5x minus 1. So yeah, whenever you do the loop to a logarithm, the loop is used to rewrite it as an exponential. So the log is no longer there. Just like whenever we used the loop earlier on the exponentials to rewrite as a log. Right? So the loop either takes away or creates a log. Alright, so now we can solve. 4 cubed is 64 equals 5x minus 1. Add 1 to both sides, 65 equals 5x. And x equals 13. I could check my answer by plugging that 13 back in. That'd be 5 times 13 is 65, minus 1 is 64. So that's a positive number. So 13 will work. Alright, so remember to check for extraneous solutions. Okay, logs of negative numbers aren't defined. That doesn't mean a negative solution isn't the answer. It means that if you plugged a solution back in and you would be taking the log of a negative, that can't happen. That's not defined. So we always have to plug our answers back in. Alright, in this example we have log of 8x plus log of x minus 20 equals 3. So the very first thing that we need to do, since we have two logs of the same base being added together, we need to condense the log. And the reason that we're condensing is that we can just have one logarithm. Okay? So if you have two logs with the same base being added together, what do you do to the things inside the log, the 8x and the x minus 20? How do you combine them? You multiply. So the addition of two logs, you multiply the things that you're taking the log of. So this is the log of 8x times x minus 20 equals 3. Okay, now you're actually going to need to multiply those. So we have the log of 8x squared minus 160 is equal to 3. Now that we've condensed the log, okay, and we just have this log isolated, I'm ready to do the loop. And I have to do the loop because I have a log only on one side of the equation. So what's the base of my loop?
10.
Yeah, this is a base 10, okay, because it's a common log. So from the loop I see 10 to the third power is equal to 8x squared minus 160. Okay, 10 to the third power, just like we saw at the very beginning of the lesson, is 1,000 is equal to 8x squared minus 160. Oh, and what have I missed on these past three lines?
You didn't put the x.
Yeah, the x goes on this 160 as well, because you're distributing an 8x. So, sorry about that. Alright, now that I have an x squared and an x, I'm going to have to set everything equal to 0, factor, and solve. So I'm going to subtract the 1,000 from both sides. 8x squared minus 160x minus 1,000 Luckily, all of these things are divisible by 8. So I can say 0 is equal to 8 times, just divide each of these things by 8. That'd be x squared minus 20x minus 125. So now I need two numbers that multiply to negative 125 and add to negative 20. So that's going to be x minus 25 times x plus 5. So if these are factors, what are my solutions? You said each thing equal to 0, so
X minus 25.
8 equals 0, that's not a solution. X minus 25 equals 0, that gives me x equals 25.
And X equals negative 5.
And x equals negative 5. Okay, so let's check our solutions to make sure that we wouldn't end up taking the log of a negative. Okay, 8 times 25 is positive, so that would work. 25 minus 20 is positive, so 25 works. Now let's check negative 5. 8 times negative 5 is negative 40. You'd be taking the log of a negative. That can't happen, so this is extraneous. So my only solution is x equals 25. All right, let's just do one last example together. 3 log base 8 of 2x plus 7 plus 8 equals 10. I need to get this logarithm by itself. So what do you think is the first step? The first thing I need to do is get rid of this 8. So now I have 3 log base 8 of 2x plus 7 equals 2. Now, still trying to get this log by itself, I'm going to divide both sides by 3 to get rid of this 3 in front of the log. So I have log base 8 of 2x plus 7 is equal to 2/3. Oh, look, we got a log by itself on one side. I'm ready to do the loop. Because, again, that's just because you can't take the log of a variable. So 8 to the 2/3 is equal to 2x plus 7. Remember, whenever you raise something to a power like 2/3, that'd be squaring the 8 and then taking the cube root. So 8 squared is 64. The cube root of 64 is 4. So this equals 4. 2x plus 7. Subtract 7 from both sides. So we have negative 3 is equal to 2x. Dividing by 2, we have x equals negative 3 over 2. Okay, so we have a negative. We definitely want to make sure that we check our negatives to make sure if it's extraneous or not. So if I plug negative 3 over 2 back in, what's 2 times negative 3 over 2? It's negative 3. So negative 3 plus 7 is positive 4. Would you be taking the log of a negative?
No.
No. So this is my solution. It's not extraneous. All right, sorry for the long notes, but that's everything about solving logs and exponentials.